For the second and final part of this unit, we're going to talk about entropy and free energy. Entropy is the degree of disorder. It's represented with the symbol S. I know, there's no S in entropy, but we should be used to this by now in chemistry. Matter changes from a more ordered to a less ordered state. I like to think of this using analogy of cleaning your room. It is far less work and less energy to just throw your stuff on the floor. Take off dirty clothes, put them on the floor, throw your books on the floor, leave your bed unmade. It takes far more energy to keep it neat and ordered. You have to actively make your bed. You have to actively fold your clothes. You have to actively put things away. And reactions are much the same way. They're sort of lazy, and they would like to go to a less ordered state. It takes a lot of energy to stay in an ordered state, and so they prefer or favor disorder. So if we look at this reaction, entropy here is increasing. We're going from 2 molecules of water, and it's splitting apart to hydrogen and oxygen. Anytime we split apart from one type of molecule to multiple types of molecules, we are increasing the entropy. We also increase the entropy by changing states. A solid is very ordered and therefore very low entropy. A gas has a lot of disorder and therefore a lot of entropy. So when we go from hydrogen that's a liquid to hydrogen that's a gas, again, entropy is increasing. A positive delta S, or positive, means there's an increase in entropy. Okay, so both of these reactions would have a delta S that is positive because both of them are increasing in entropy for different reasons, but still increasing. In terms of entropy calculations, if the reaction increases in entropy, delta S is positive, and the reaction is said to be entropy favored. There'll be more on this in a minute. So it says calculate the entropy change, delta S, for the following reaction. It's the same thing that we did with enthalpy. And again, Gibbs free energy, which we're going to talk about in a minute, is exactly the same thing. Our reaction, our overall reaction, which I'm going to put up here because I didn't leave myself much room, is delta S is equal to the sum of the delta S of the products minus the sum of the delta S of the reactants. So it's products minus reactants again, just like we did before. And we need to refer to the table in your book, in your packet, to do this. But what we're doing essentially is 2 times the CO2, which is gaseous, that's my product there, plus 2 times the H2O, liquid, which is there, minus, big square, CH4, gas, plus 2 times the O2 gas. In this case, the states of matter are very important because we need to choose the proper ones off of our table. So H2O liquid and H2O gas are both listed, and so we'll have to choose the right ones. So follow along with me and make sure you can find and choose the proper ones. But I'm going to have 2 times 213.74. Notice my units is joules per mole Kelvin. It's listed at the top. Plus 2 times 69.91 joules per mole Kelvin minus 186.264 joules per mole Kelvin plus 2 times 205.138 joules per mole Kelvin. This ends up being, when I simplify, delta S is equal to, everything in this bracket ends up being 567.3 joules per mole Kelvin minus everything in this bracket ends up being 596.54 joules per mole Kelvin. And I end up, I wish put that in square brackets, with a final answer of negative 29.24 joules per mole Kelvin. And so this entropy is negative, and therefore this is not entropy favored. This reaction still does occur, but it's not entropy favored. Think about, we're going from 3 moles of gas to 1 mole of gas and 2 moles of liquid. So that's not going to be favored in terms of increasing entropy. It's actually decreasing in this case. Gibbs free energy is what lets us know if a reaction is going to be spontaneous or not. So it's a measure of the chemical reaction potential of a system. And this is the important part that you need to take away. If delta G is negative, the reaction is spontaneous. If delta G is positive, the reaction is not spontaneous. I don't have any tricks to remember that, just that you do need to know that information. You calculate delta G one of 2 ways. The first way is to use the table and do products minus reactants, just like we did for enthalpy and entropy. So this whole unit can be summarized as products minus reactants, sum of the products minus sum of the reactants. So it wants us to go ahead and calculate the change in free energy for the following reaction. So, just like we did earlier for our reaction, delta G is equal to 2 times the CO2 gas plus 2 times the H2O liquid minus my reactants, which ends up being CH4 gas plus 2 times the O2 gas. It's the exact same equation that I did before for entropy, except I'm going to fill in the delta G values. So delta G is equal to 2 times negative 394.359 kilojoules per mole plus 2 times negative 237.129 kilojoules per mole, and that's that side of the reaction, minus a minus 50.72 kilojoules per mole, and plus 2 times 0 kilojoules per mole. And then I'm going to go ahead and simplify all this. Biggest mistakes made in any of these problems is remembering to account for the negatives properly. I will want to see this step. I want to see your substitute in steps so that I can give you partial credit in case you do your math wrong. So delta G ends up being equal to negative 1269.976 kilojoules per mole minus a minus 50.72 kilojoules per mole, which is equal to negative 1212.2, it's a decimal, 0.256 kilojoules per mole. I know this is a little hard to read. This is a decimal here. 1212.256. Notice that it is negative, and this reaction is spontaneous, which makes sense. It's a combustion reaction. So even though it's not entropy favored, overall the reaction is spontaneous, because once we catch this on fire here, this reaction is going to proceed spontaneously. And this is probably the most important slide of the whole unit. You're going to need to be able to know and understand this. So enthalpy and entropy can be combined to predict a reaction's spontaneity. We can use our table, although we can use our table to directly calculate delta G, it is also related to enthalpy and entropy. So if we calculated these values, we can find this one. The thing to remember if we are doing that is that these two are measured on our table in kilojoules, and entropy is measured in joules. An important thing to note because they all have to be in the same unit. And so we need to look at this chart here. I'm going to erase those for a second because we need to understand this chart. This is the important part of sort of what ties this whole unit together. If my reaction is to be spontaneous, delta G has to be negative. And so if delta H is a negative number and delta S is a positive number, and temperature is always going to be in Kelvin, so temperature is always a positive number. If this is negative and we multiply a positive number times this, so we have minus and then we're subtracting another positive number, our delta G in this case has to be negative. And therefore, a reaction that's exothermic with an increasing entropy will always be spontaneous. Let's go down to case number 4, the last case, and look at that one. If delta H is positive and delta S is negative, there is nothing we can do to make this reaction spontaneous. It will be a positive number here, and then minus a negative will make this positive. Delta G will be positive, and this reaction, because delta G is positive, is never spontaneous. So to me, those are the two easy ones to understand. Now let's look at our two middle conditions. In this case, it's an endothermic reaction, so this is positive. But my entropy is increasing. So when will this be positive? Well, delta G in this case could be positive or negative depending on what this temperature is. If this temperature sort of drives this so that this is larger, because remember this is the negative value here, then it'll be spontaneous. If this temperature is small and it ends up being that this side is bigger, my delta G will be positive. So this will be spontaneous at high temperatures. If I can make this factor here, T delta S, greater than delta H, my reaction will be spontaneous. If I look at this and delta H is negative, so it's exothermic, and entropy is decreasing, what I need is this factor now to dominate. And so if this T stays very low, if this stays to be a very small number, then this value here will be bigger than this value here. And as long as this value is bigger and it's negative, my delta G will be negative, and so it'll be spontaneous at low temperatures. And you might want to revisit this slide or this idea. You will need to know how to fill this chart in for your test. You will need to be able to answer questions based on this chart. So this idea is going to be very important for this unit.